Hi, we are Adib Islam, Victorian Turner, and Chongji Lee from Team 4. This is our progress presentation. Our goal with this project is to improve upon the Dreamer paper. Just to recap, Dreamer is a model-based reinforcement learning algorithm that learns a world model from images and learns a controlled policy to interact with the world. Our world model enables us to predict how the world, i.e. the environment, changes conditioned upon the action of an agent. Having learned a world model, we can predict or imagine in latent space and learn a policy network by backpropagating the rewards obtained in imagination. We identified some limitations of the Dreamer algorithm and focused on a few of them to improve on. Learning an imperfect world model during early learning stage can result in improper planning and policy. Thus, the samples collected would be limited to the poor interactions in the environment and the agent learns a locally optimal solution. This becomes an issue when we want to learn a hard task such as powerlifting in the humanoid benchmark environment. Thus, we plan to implement curriculum learning to train the agent on easy tasks and then gradually train on harder tasks. We also identified that the gated recurrent unit used in Dreamer for world modeling can lead to long-term memory loss. Thus, we decided to replace the GRU cell used for modeling with the MUMB architecture. We believe that this will enable us to solve complex tasks that requires long-term planning. Our goal is to improve upon Dreamer v3 and to solve hard tasks such as basketball and hang bar in the humanoid benchmark simulation environment. We faced several issues so far. We were able to successfully train Dreamer v3 on simple singular tasks like sitting using only joint angle states. Unfortunately, we are having some difficulties integrating the image observation from the humanoid benchmark environment into the Dreamer v3 training pipeline. We also started working on the curriculum learning training pipeline and we realized that we need to decide on the measure of difficulty. We decided that it shouldn't be something arbitrary like our intuition. Instead, it should be based on the reward obtained from the task. However, different tasks have different scale of rewards, making it hard to naively use environment rewards to design the curriculum. Furthermore, we think that there is a good probability that the agent could forget previously learned simpler tasks like sitting while learning complex ones like running. To that end, we plan to experiment with task condition learning so that the agent can associate a given motion primitive to a task label. Finally, we came to the conclusion that integrating constrained RL and safe exploration ideas into Dreamer is beyond the current project timeline, so it will be a topic we will explore for future work. We are on track with our original timeline, having almost finished replicating Dreamer v3 training on simple tasks. We have also started working on calculating the task difficulty evaluation metric, which will be used to design the curriculum learning training pipeline. Work is in progress in studying how to replace the GRU cell with Mamba.
In this section, we will focus on the implementation of curriculum learning. As we explained earlier, this technique is implemented to enable better convergence by avoiding local extremes and to enable faster learning by reaching higher rewards for the same number of iterations. One reason why the model may fall into a local optimum is that each task is learned independently and doesn't reuse learning from the other tasks. Similarly, the model is slow during learning since for each task, the model is trained from scratch. Integrating curriculum learning allows tasks to be learned sequentially, reusing learning experience from previous tasks. However, to make learning easier, we need to learn the simplest task first and gradually increase the difficulty. That's why we have created a benchmark to evaluate the difficulty of 29 tasks available in the simulation. These tasks can be, for example, walking, sitting, or throwing an object. The evaluation is based on the reward curve obtained over 1,000 training iterations on the 29 tasks. The idea behind difficulty evaluation is that the more iterations a model requires to learn a task, the more complicated the task is. To achieve this, we need to define metrics that will determine the difficulty of each task and therefore the order in which they are learned. Before defining the metrics, an important step was to normalize the reward curves. As we can see, the rewards are not homogeneous for one task to another. What I mean is that the maximum reward is not the same for all tasks. We therefore need to normalize them to the same interval for comparison purposes. The first metric consists of evaluating the area under the curve. This area represents the cumulative reward over time. A model that manages to approach its maximum reward quickly will therefore maximize this area and therefore maximize the value of this metric. As the example shows, the high bar task is difficult to learn since reward growth is slow and occurs late. That's why the area under the curve is low. In contrast, the insert small task is easy to learn and has a higher area under the curve. The second metric considers that the simplest tasks to learn are those that allow the reward to evolve rapidly. To achieve this, it consists in calculating the mean value of the gradients. The gradient values are weighted so that the values of the first iteration counts more than those of the last, and this linearly. The aim is to favor curves that increase in value from the very first iterations. In the example, the red rectangle represents the number of iterations required before the model shows a significant gain in reward. We can note that the difficult task has a larger red rectangle. The last metric considers that the simplest tasks to learn are those that reach higher reward rapidly. It consists in calculating the index for which 90% of the maximum reward is reached. We then calculate the ratio of the index over the number of iterations. The higher the ratio is, the more complicated the task is. Difficulty ranking is calculated for each metric, followed by an overall ranking. The experimental results seem very consistent with the visual aspects. We will now use this ranking to order our training.
Lastly, we will talk about long-term improvement. At SMSF-GLU struggle with maintaining long-term information due to its limited state size. We selected Mamba for its low memory requirements, efficiency, and the selective state space mechanism, which selectively retains or forgets information based on input. Mamba's design effectively handles long-term dependencies, making it an ideal choice for enhancing Dreamer. To integrate Mamba into Dreamer, we replace RSS with non-RLM inputs are processed by Mamba. Mamba directly refers past states, improving long-term performance. Dreamer has 6 components with the deterministic and representation model dependent on hidden state. Our approach removes this dependency like table. This structure shift and Mamba's selection mechanism are expected to enhance long-term performance. While applying Mamba to Dreamer, we addressed the challenge of adapting the encoder. Unlike Dreamer, which processed input sequentially for hidden state, our model processes our inputs simultaneously. To resolve this, we redesigned the encoder to handle multiple inputs at once. Our Mamba-based structure faced higher computational due to processing all states simultaneously. To address this, we modified Dreamer's imagination trajectory generation by sampling a small subset of starting states from the reply buffer. A current challenge is adapting Mamba for Human Bench, which uses JAX. Since Mamba was implemented in PyTorch, we are working on converting its code to JAX. To ensure fair performance comparison, we aim to match the parameter size of Dreamer's world model with our Mamba-based structure. Since Mamba uses a block-like architecture, we plan to connect Mamba blocks to achieve a similar model size before evaluating performance. To validate Mamba's long-term benefit in Dreamer, we explored other tasks, emphasizing memory such as ordering colored balls in the room. In Human Bench, we identified challenging tasks like powerlifting and kitchen, targeting those with the longest action sequence for curriculum learning. For the math task, we propose adding ordered goals like image. Mamba is expected to improve stability and speed in long-term task learning, further enhanced by curriculum learning. This concludes our presentation. Thank you.